Hey guys, here is part 2 of the 3-part video explaining exercise 14 from section 2.1. So the setup is two vector spaces V and W and a linear transformation between them. Part B asks us to show this. If we suppose that T is 1 to 1 and that S is a subset of V, then we can prove that S is linearly independent if and only if T of S is linearly independent. So let's jump in here. Part B, let's look at the forward direction. What is this actually asking? So we're supposing that T is 1 to 1 and S is any subset of V. Then we're going to show that if S is linearly independent, then T of S is linearly independent. But that's exactly what we proved in part A. In part A, we showed that if T was 1 to 1, then if we had any linearly independent subset of V, then T would carry it to a linearly independent subset of W as well. So this forward implication of part B, this is exactly part of what we proved in part A. So we're done. We don't have to prove that again. We already proved that if T is 1 to 1 and you start with a linearly independent subset in V, then the transformed subset, T of S, is also linearly independent in W. So the content of exercise B is the reverse implication, namely that if T of S is linearly independent in W, then S is linearly independent in V. So now we've got our supposition. Suppose that T is 1 to 1 and S is a subset of V. We will suppose that T of S is linearly independent in W, and we will show that S must be linearly independent. All right, well, to show that the set is linearly independent, we have to show that the only way of representing a zero vector is the trivial way. So suppose that A1 V1 plus A2 V2 up through, let's say, AK VK is equal to the zero vector from V. For some A1 through AK in the field and V1 through VK in S, right? The vectors from S. We want to show that the only way this can happen is if each of these AIs is 0. Well, what we know is that T of S is linearly independent. So if we were to apply T to each of the vectors VI, then those vectors would be linearly independent. So we need to somehow get some relation about the T of these vectors. Well, if this equation holds, then this whole left-hand side vector is equal to this whole right-hand side vector. And following the old adage from all of mathematics, as long as you do the same thing to both sides of the equation, things should work out. So if I applied T to the vector on the left, that should be the same thing as if I apply T to the vector on the right. But now by linearity, we know that T applied to this linear combination is a linear combination of these transformed vectors. And we know that a linear transformation sends the zero vector from V to the zero vector from W. So now we actually have a linear combination involving the vectors T of S equal to the zero vector, since T of S is linearly independent, each of the coefficients in this expression must be 0. But of course, these are the coefficients that we started with when we were describing the 0 vector using vectors from S. So really what we've shown is that if we start representing the 0 vector using vectors from S, the coefficients we used must all be 0. So we conclude that S is linearly independent, which is the thing that we wanted to show the other implication. The first implication was free. So we've now proven part B that if T is 1 to 1, then S is linearly independent if and only if T of S is linearly independent.